Hello. Today we're going to take a look at Cramer's rule. Cramer's rule is a procedure for calculating the solution to a set of linear simultaneous equations. The method has some strengths. 1. It's simple to remember. 2. The formulae are easy to calculate by hand for 2 or 3 unknowns, and easy to implement in spreadsheets and computer programs. And 3. It allows the calculation of 1 or more of the unknowns without necessarily having to calculate them all. But there are a couple of weaknesses to the method. Firstly, it's very cumbersome to use this method by hand for more than 3 unknowns, and inefficient, even by computer, for larger systems. Secondly, there can be stability issues that mean you may need to hold intermediate calculations to high precision. We'll start by solving the 2 by 2 case, 2 equations, 2 unknowns, by hand. This is not a proof of Cramer's rule, but at least suggests what the rule might be. Then we'll prove the rule. We'll do so with 3 unknowns, but the proof works for any number of unknowns. We'll do an example and finish with an exercise, which will demonstrate the stability issue. For the 2 by 2 case, let's have ax plus by equals p, and cx plus dy equals q. Let's also define C to be the matrix of coefficients. In other words, C is A, B, C, D, and define N to be the vector of constants, P, Q. We'll also define CXN to be the matrix C, but where column X, the first column, has been replaced by vector N. In other words, P, B, Q, D. Similarly, CYN is matrix C, where column Y, the second column, has been replaced by vector N. In other words, A, P, C, Q. Now we multiply equation 1 by D and equation 2 by B to give ADX plus BDY equals PD, and BCX plus BDY equals QB. Subtracting 4 from 3 gives x into AD minus BC equals PD minus QB. So x equals PD minus QB over AD minus BC, which we can write as the determinant of PBQD over the determinant of ABCD. We can write this as the determinant of CXN over the determinant of C. To find y, we multiply equation 1 by C and equation 2 by A to give ACX plus BCY equals PC, and ACX plus ADY equals QA. We then subtract equation 5 from equation 6 to give y into AD minus BC equals AQ minus PC. So y equals AQ minus PC over AD minus BC, which we can write as the determinant of APCQ over the determinant of ABCD. In turn, we can write this as the determinant of CYN over the determinant of C. While this isn't a proof of Cramer's rule, it's certainly suggestive of the result, which is as follows. If we have a system of linear equations, a1x plus b1y plus c1z, etc., equals p1, a2x plus b2y plus c2z, etc., equals p2, and so on, then x is equal to the determinant of cxn over the determinant of c, where c is the matrix of coefficients, n is the column vector of p1, p2, etc., and cxn is the matrix formed by taking c and replacing column x by vector n. The result for y, z, etc. is similar. To prove this result, let's consider a 3 by 3 system. Then matrix C is A1, B1, C1, A2, B2, C2, etc. Now consider x times the determinant of C. Now multiplying a determinant by a scalar is the same as multiplying all the elements of any single row or column by that scalar. So our expression is equal to the determinant of a1x, b1c1, a2x, b2c2, a3x, b3c3. Next, recall that a determinant is unchanged if we add a multiple of any column to another column. So here we add y times column 2 to column 1 to give a1x plus b1y, b1c1, a2x plus b2y, b2c2, etc. We do this again, this time adding z times column 3 to column 1 to give a1x plus b1y plus c1z, b1c1, etc. But looking at the first column, each entry is the left-hand side of the given equations, so we can replace them by p1, p2, p3. In other words, the expression is just the determinant of cxn. Dividing through by the determinant of c gives the result, and the results for y and z are similar. Now let's do an example. Suppose we're given the set of equations x plus y plus 2z equals 7, 3x plus y minus z equals 9, minus x plus y plus z equals minus 3. Then c is 1, 1, 2, 3, 1, minus 1, minus 1, 1, 1, and n is 7, 9, minus 3. Replacing the first column of c with n gives cxn as 7, 1, 2, 9, 1, minus 1, minus 3, 1, 1, and similarly for cyn and czn. We won't go through the arithmetic here, but you can verify that the determinant of c is 8, of cxn is 32, of cyn is minus 8, and czn is 16. That means that x, which is the determinant of cxn over the determinant of c, is 4. Similarly, y is determinant cyn over determinant c, which is minus 1, and z is determinant czn over determinant c, which is 2. Finally, let me leave you with a question to try. Solve x plus 2.001 y equals 5.002. 1.999x plus 4y equals 9.999. If you follow the above method, you should get x equals 1 and y equals 2. But you might also like to try doing all computations to 4 decimal places. If you do so, you'll get the wrong answer. Even though the numbers in this problem extend to only 3 decimal places, to get the right answer, you'll need to work to 6 decimal places. This illustrates the stability issues that sometimes arise with Cramer's rule, and the problem can get worse with larger systems.